Hi everyone, myself Dr. Sushnata Pramanik. I am Assistant Professor in the Department of Chemistry, SRM Institute of Science and Technology, Cotton Cloth Campus, Chennai. Today we are going to talk about aliphatic nucleophilic substitution reaction. So throughout this discussion, we will be first I'll be talking, introduce you what is substitution reaction. Then I will discuss different types of mechanism, for example, SN2 and SN1. Then I'll be talking about the reactivity of the different carbon centers and nucleophile, followed by a solvent effect or solvent polarity effect on the reaction rates. At the end, we'll be discussing about the leaving group. For this, I followed mainly these two books. One is the March Advanced Organic Chemistry, 7th edition, edited by Michael B. Smith, and another one is Organic Chemistry, 2nd edition by Graydon, Graves, and Warren. So, what is substitution reaction? So, if you see the definition, a substitution is a replacement of one by another. If you say, if you take an example, like you are sitting on a chair and one of your friends come and replace you and he or she sits on that chair, so you are actually replaced by your friend. Okay, so in chemical reaction or in organic chemistry, substitution reaction is one of the important reaction that people use in making big molecules, for example, big drug molecules. So in a particular substitution reaction, in this particular scheme, whatever you can see that the carbon which is attached to a bromine atom, and then you have a hydroxyl anion or hydroxyl group which actually substitute the bromine and it forms the alcohol compound, and the bromide is the leaving group. Okay, we call this hydroxyl group as a or hydroxyl anion called nucleophile, and it means that affinity towards nucleus. And why it is so? Because it is actually uh, we know that nucleus is a positive charge, okay, because it has a protons, yeah, and then this nucleophile having a negative charge, so positive and negative they can interact with each other, so that's why it is called affinity towards the nucleus. Then we have this carbon which is called electrophilic centered, which is, in other words, we can also say it has affinity towards the electrons because the nucleophile having electrons. And then we have a leaving group that leaves the molecule. So these are the three important terminology we should know for the nucleophilic substitution reaction. So what are the nucleophiles? So nucleophiles are those which having or which possess a pair of electrons which brings to the substrate. Okay, so here in this case the OH minus group has actually the O oxygen atom has 3 pair of electrons, so one of these can be donated to the substrate here. Okay, so there are different kinds. You can see these are the neutral ones where you have amine, water, or thiol are the examples of neutral nucleophiles. So here you can see nitrogen have a pair of electron, oxygen has 2 pairs of electron, and sulfur also has 2 pairs of electron. It could be an ionic species, for example, X is a halide. So here we have seen that halide could be a leaving group as well. So eventually the halide can act as a nucleophile as well as leaving group depending on the situation or the condition you have used during the reaction. You have a hydroxyl anion which can also be a nucleophile, sulfide, S minus, azide, etc. Okay. Now, before going into details, we would like to talk about the types of substitution reactions. So there are 4 different types, and if you see those schemes, you will find that there is actually so that in the left hand side and the right hand side of the reaction, there's some change in ionic character of the molecules or the anions. So in the type 1, you can see that your substrate is neutral, but your nucleophile is an ionic species, and in the right side you have a product is a neutral, but leaving group is the anionic species. Similarly, in type 2, you can see you start with a completely neutral species, both the substrate and the nucleophile, but at the end you end up with a positively charged product as well as negatively charged leaving group. In type 3, you can see you have a positively charged substrate and negatively charged nucleophile, and then both becomes neutral after the reaction. In type 4, you have a positively charged substrate and then neutral nucleophile, and you have a positively charged product and the neutral leaving group. Now, why we should know all this? And this is because you are changing the ionic character in the reaction mixture. Therefore, if you use a solvent which has different polar effect, you can actually control the rate of the reaction. For example, so this is actually solvent plays more important, play very much important in these reactions. If you see in the first case, in the left hand side and the right hand side, both are having one negative charge. So basically, or theoretically, you can think that we may not have any sort of solvent polarity effect because there is no net change in the charge. However, if this nucleophile, so we'll come back to that later, if this nucleophile is important in or involves in the rate determining step, so if you use a polar protic solvent, that may reduce the rate of reaction. So we will come back to that later. In this case particularly, if you can see, we have both substrate is ionic and this nucleophile is also ionic, but your products are actually neutral. So therefore, if you use a non-polar solvent which can stabilize your product, you can speed up the reaction. On the other hand, here in type 2, you have both neutral species, but your products are actually ionic. So therefore, you should use a polar solvent, which means that polar solvent will stabilize your products and the leaving group, and you can speed up the reaction. So this is very like generalized way to think about the reactions, but when you go to the deeper into the mechanism, we will find that sometimes they may not follow as we have discussed right now. Okay, in 1930s, Hughes and Ingold first find out that there are certain substitution reactions are first order and certain substitution reactions are second order. So here I have listed out two different reactions. So you can see in the first case, again, I have taken alkyl bromide and hydroxyl anion as a nucleophile, and you have alcohol, so I omit the leaving group. In the second case, you can see again the tertiary bromide react with the hydroxyl anion, and you got the tertiary alcohol and the leaving group I didn't write. Okay, so in the first case, whatever they found is that the rate of the reaction is actually depends on both the substrate S, which is the alkyl bromide, and the nucleophile. In the second case, what they found that the rate of the reaction only depends on the substrate. So because it depends on both the or two different molecules, these are second order reactions, and because it depends only one molecule, so we call it a first order reaction. Okay, so the first category, it is actually known as substitution, or it is termed as substitution nucleophilic biomolecular or bimolecular, not biomolecular, bimolecular. So that is denoted as SN2. And the second one, substitution nucleophilic unimolecular, that is also denoted as SN1. Now you see here the difference in the substrate structure. So first one is not that much bulky, and the second one is very bulky. So when we will be discussing these mechanisms in detail, we'll be discussing what is the role of this branch structure in determining the different rates of different mechanism. Okay, first we are going to talk about the substitution nucleophilic bimolecular, so SN2 mechanism. In case of SN2, it is very much important is that the nucleophile is actually coming from the backside of the carbon-bromine bond, or in other words, carbon and leaving group bond. And why it is so? If you see the orbital picture of the bonding orbital of the carbon-bromine bond and anti-bonding orbital of the carbon-bromine bond, the anti-bonding orbital is actually opposite to the carbon-bromine bond. Okay, so here the orbital coefficient is more, and the nucleophile is actually attacked at the antibonding of the carbon leaving group. So therefore, in case of SN2 mechanism, the nucleophile always has to come from the back side of the leaving group. Okay, so this is the transition state of the reaction where you can see the carbon is hypothetically pentavalent and the R hydrogen and deuterium. Here R is actually any aliphatic chain. It could be methyl, ethyl, isopropyl, even butyl as well. So that we will come back later. But in general, any aliphatic substituents we do denote is as a R. Okay, so here you can see the R, H and deuterium, they are actually in one plane, and the other one, OH, carbon and bromine, they are actually in the linear. Okay, so if you have the plane of R, hydrogen, deuterium like perpendicular to this screen, and then your OH, carbon, this is the carbon center, and the bromine, they are in the linear element. Okay, so this is actually denoted within the third brackets with a dagger sign as a superscript, and this is known as transition state. Okay, and then after the reaction you can see the bromide comes out and the OH actually attached to the molecule. Okay, so what is the energy diagram? So in this energy diagram, what you can say is that your first is the starting material where the reaction start to proceed towards that transition state, and at the transition state the leaving group, the carbon bromine bond stretch out slowly, more the stretch out, and the OH and carbon bonds becomes shorter and shorter, and finally you got a pure bond and the bromine leaves the molecule as a Br minus. So this is a one step reaction, so it is one elementary step, so therefore this should be the rate determining step. Okay, there is no other step, so you can just close your eyes, then you can say this is my RDS. Now this is very important here because this is the RDS where your nucleophile as well as substrate both involves in the rate of the reaction. Okay, so in the rate determining step, so that's why it is called substitution nucleophilic bimolecular reaction. Okay, so this is the activation energy whatever it is required, and we generally say is EA, which is activation energy, or delta G dagger if you want to express your energy in terms of Gibbs free energy. And this is very important because if this is very high, your reaction will be slow or it may not occur at all. Or if it is very low in energy, if the delta E value is very that EA activation energy is very small, then you can perform the reaction at very mild condition or at even the room temperature. Okay, so let's talk about something else, that how you can prove that my reaction is actually depends on both. So for that, what you have to do is that you can, so for this particular case, you can keep the substrate concentration constant, and you can vary the concentration of the nucleophile. And if you measure the rate, you will find that with the increase in the concentration of the nucleophile, your rate should increase linearly. So the slope for this case should be the K into concentration of the substrate, because if substrate concentration also you kept constant, you are changing only the concentration of the nucleophile. On the other hand, if you keep changing the concentration of the substrate, keeping the nucleophile concentration constant, you will also see there is a linear increase in the rate with increasing the concentration of the substrate. So this experiments, both experiments combinedly prove that the rate of the reaction actually depends on both your nucleophile as well as substrate. Now the slopes I have drawn differently, so this is very hypothetical assumptions. It could be completely different as I have presented here. Okay, so what is the stereochemistry? So if you start with a carbon center which having a chiral center, okay, so what happened to that particular chiral center after performing the SN2 reaction? So what I have told you earlier is that your nucleophile should come from the backside of the carbon bromine bond. Okay, so so if you do that, and then your OH group should be coming on the other side. Okay, so let's try to check what is the stereochemistry of this particular carbon. So R is aliphatic. So if you follow up, if you know that CIP rule, Kahn, Ingold, and Prelog rule, and there the bromine should be the first priority. Then then you have a alkyl chain, and then will be the deuterium, and the hydrogen with the least priority group. Now, if you put that carbon hydrogen bond behind you or further away from you, and you can see, so you have 1 2 3, which is actually the anti-clockwise rotation, and therefore the priority should be the S. So what about the after the reaction? Now if you count again, so your OH becomes first because that should have a higher priority compared to the any carbon chain. So this is 1 2 and 3, so you should have R priority. So basically if you perform a substitution reaction in a chiral center, you should substitution in the sense that SN2, if you perform a SN2 reaction at a chiral center, you should always see inversion of priority. So that is we call inversion of priority. Now one thing I would like to mention over here is that the priority rule, your leaving group and your incoming nucleophile should have the same priority. If they don't follow that, you may end up with the S again after the reaction. But in reality, you should always see inversion of priority. Okay, so if for example here I have said 1, your incoming nucleophile, it may happen this becomes 2 and this the R becomes 1, then again you have the anti-clockwise rotation. So that's what I was saying, that the priority rule should maintain, okay, to understand easily. So that's why I kept the examples where the bromine and the OH having the first priority. Okay, so we should prove it. Like now here I have explained you it should come from the back side of the carbon and leaving group, and we should have inverse chirality. But if you cannot prove it, then there is no use of it. Okay, so people always, because as is in the scientific community, you should give the proper data to prove your hypothesis. Okay, so for that you should also perform a like a reaction, and then you should have a data or experimental data that prove that yes, there is inversion of chirality. So for that you can actually perform this particular reaction. So this is the S2 butanol. So here you can see the OH in the top side or above the plane, and I have one ethyl group and the methyl group on the plane, and then you can react with tosyl chloride in presence of pyridine. You just tosylate the OH group. So tosyl is actually that para-toluene sulfonic acid. Okay, pardon me. So now what in the first case you did not do anything at the carbon center, you only react at the oxygen, so the chiral center should not alter at all. Now you are doing the SN2 reaction, so where you react with the acetate anion, so the acetate should come from the back side and your OTS should leave the molecule, yes, so your OTS was on the above the plate. Now you perform the SN2 reaction, so the OAC or acetate should come from the bottom of the plate. So you end up with this particular product. Now what you can do is that you hydrolyze the acetate group in presence of sodium hydroxide. So now you treat with mild sodium hydroxide, because if you use strong sodium hydroxide, again you can perform the SN2 at this particular carbon. Okay, so you should use a very mild or dilute solution of sodium hydroxide. This will attack at the acetate group or this acyl group, and then after electronic rearrangement, the OAC minus OAC group or acetate should leave the molecule, and you end up with the corresponding OH group again. So now you can see here that your OH, which was at the above the plane, now it goes down the plane. Okay, so you actually invert the chirality. Now what you should do, you should measure the optical rotation. Now optical rotation is actually experimental method to identify the molecule is chiral or not. Okay, so if you have a S butanol, for example, whatever value it should give in optical rotation, it could be like clockwise rotation or anti-clockwise rotation, so plus or minus. You should learn it in a different topic, so we'll discuss it later on if we prepare another video on that. So whatever the the S isomer have the optical rotation, the R isomer should have exactly same value but opposite sign. So for example, if you have plus 30, you should have minus 30 for this. Now you know for your starting material what is that. Now if you have this product as a pure, okay, it means during the course of this reaction you may not get quantitatively 100% of this. If you have mixture of this, that is a different scenario. If you have only this compound, then that plus 30 whichever you have found here, for this particular compound you should have minus 30. Okay, so that means that these two are enantiomer, and after the reaction you alter the, or you do the inversion of the chirality at this carbon center. So let's take an example. So this is actually experimental result that performed. So again you start with the alcohol which has plus 33, which alpha is the rotation, specific rotation. You first react with the tosyl chloride in presence of pyridine. So sorry, I forgot to mention the pyridine over here. And then you do the tosylation. So you did not alter anything at the carbon center. Then you actually treat this molecule with ethanol and potassium carbonate. So what they do, this potassium carbonate will take the proton, you produce the ethoxide ETO minus. So that is a good nucleophile, and then you perform SN2 reaction and you get this particular compound. Okay, so what happened here, you actually after this SN2 reaction you should get that the optical rotation minus 33. Now you can do the another reaction, which is because to prove that it is actually, because if you change that the substituents, okay, so here you have OH, here you have OET, it could have a completely different optical rotation. Okay, so that's why you should also prepare a similar compound but opposite chirality. Okay, so you do that first you treat with the sodium hydride, you do that first you make the O minus, okay, and then you react with the ethyl bromide. So this O minus is a nucleophile now and you're reacting over here, so but you do not alter anything at the carbon center, and therefore you should retain the chirality and you should have the plus 33. So now you can see that your one enantiomer having minus 33 optical rotation, another one will have a plus 33 optical rotation. Okay, so this how you can actually say that you can say that sorry, that the after SN2 reaction you actually change the chirality of the molecule, or you invert the chirality of the molecule. Okay, let's talk about the how the carbon center or the substituents present at the carbon center will affect the rate of the reaction. Okay, so what we have, so this is the scheme that we already discussed. This is the transition state where your OH minus with the nucleophile is coming from the backside of the carbon bromine bond. Okay, now what does it mean is that if this R and this hydrogen and deuterium, they are changed or replaced with the bulkier group, like you have methyl groups, ethyl groups, isopropyl groups, T-butyl groups, all these if you change, how this will affect the rate. Okay, so this is a very standard reaction that is actually experimental result. So where R is denoted or whatever it is, methyl, ethyl, isopropyl and T-butyl, and they react with the potassium iodide in acetone and at 25 degrees Celsius. So this is your Ri, so iodide, alkyl iodide is your product, and bromide is the leaving group. Now when they measure the rate, so they first measure the rate of the ethyl bromide, which they take as a standard. Okay, you can take this as a standard, and for methyl you can see the rate is increased. So basically what you can see here, if you consider this particular compound, your R is actually the CH3 group, yeah? And other two are the hydrogens. For methyl all are hydrogens, which means that your backside is completely free of steric crowding, and therefore the reaction is increased. Now when you move to the isopropyl, so here R is methyl and one of the hydrogen or deuterium, one of them becomes a methyl, so you increase the steric crowding, which is the backside of the carbon bromine bond, okay, and therefore you actually prevent the nucleophile to approach the carbon center. You actually slows down the reaction more. In case of T-butyl, you can see the reaction was completely stopped. Okay, so that means that if you have a sterically hindered carbon center, you want to perform a SN2 reaction, you should not choose those substrate for SN2. Okay, you should choose the substrate something which does not have any steric groups. There are two examples. So these are actually the compounds which are completely unreactive for SN2 mechanism. For example, here in the carbon bromine bond, you can see, so backside is actually this side where you have all these carbon framework. Okay, so there the nucleophile will never approach to the carbon to substitute the bromine from the other side. So this is the same thing here. So these two compounds are completely unreactive for SN2 reaction. Okay, so let's talk about something. Is there any electronic effect? Okay, so why we should see or think about it? Because in the transition state, sorry, I forgot to put that third bracket with the dagger sign over there. But you can see here is that the carbon here at the or in the transition state actually having a partial positive charge, which means that if you have a substituents that can donate the electron to that deficient or electron deficient carbon center, you can stabilize the transition state, which means that if you stabilize the transition state, the energy will be lowered and therefore you can speed up the reaction. Okay, so which means if the energy of the transition state goes down, then what happens, your activation energy will be less. Okay, and therefore you can speed up the reaction. So here I have listed out some of the examples. Particularly you can see the same thing, RCl and Ki. Okay, so Ki is the I minus, or iodide is the nucleophile, and Cl in this case is the leaving group. So you have a butyl chloride, and you can take as a standard. So in case of methyl chloride, the reaction is speed up, and obviously the steric effect will be there. So we should also consider that in case of methyl, the steric crowding will be less, so the rate is increased. In case of isopropyl, the rate is down, that is purely steric crowding. Now when you come back to this particular case where you have allylic carbon, so double bond and then CH2, these are called allylic. Okay, so this allylic carbon is there, so that can donate the electron. So here I have shown you that orbital overlap, so that actually can take part in resonance to some extent, but this is not pure carbocation where you can donate the electron, or you can stabilize it to stabilize the transition state by resonance effect. So this is not possible. Okay, so just by it can donate the electron, and you can see how the orbital can actually participate in stabilizing the transition state, and therefore the rate was increased, okay, from almost 80 times. In case of benzene, so here the benzene having like how many p orbitals? 6 p orbitals are there, so 3 pi bonds, okay, and therefore the rate was increased more. For this particular case, what you can see, the rate was even higher. The reason is that the oxygen here, it has a 2 pair of electrons that can donate in this particular transition state. It can stabilize. At the same time, the oxygen is electron withdrawing group. Okay, so it can produce a delta positive charge at the carbon center. Now this is happened before the reaction initiates. Okay, so we have seen that this is a nucleophile. It is looking for a positively charged carbon center. Yeah, so when oxygen being the second or the second most electronegative element, so it will polarize this bond, and chlorine is also there. Okay, so the carbon will having a highly positive charge. So two effects is actually here operating. One, electron withdrawing nature that will attract the nucleophile more. At the same time, it can also stabilize the transition state. So because of these two effects, it's actually increased the rate over 900 times compared to the butyl chloride. So here I hope you understood that the steric crowding is actually retarded the reaction or slows down the reaction, and if you have a substituent that can donate the electron, it can speed up the reaction. Okay, so these are the two important messages from this particular slide. Okay, the nucleophile. So what should be the role of nucleophile in SN2 reaction? Now SN2 mechanism, not reaction, SN2 mechanism. Now so far we have discussed about the carbon center, the electronic effect and everything, and we also discussed that our nucleophile actually involves in the redetermining state. Okay, so which means that if your nucleophile actually plays a very important role in the rate of the reaction. if your nucleophile is good, okay, if it is reactive, then it should speed up the reaction. If it is not reactive, it's a bad nucleophile, okay, then the reaction should be very slow. Yeah, because that is involved in the RDA. So the property of the nucleophile will play a vital role in the rate of the reaction. So take an example here. So here we have a hydroxyl anion, then we have a acetate or carboxylate, we have a water and the sulfonate. Okay, now here I have listed out the pKa. Now hydroxyl, this is the water pKa is 15.7, acetic acid like 4.76, and then you have a water which is H3O plus is minus 1.7, and this is sulfonic acid which have almost 0. The question is that by definition of acidity, we should know, or we know that the higher the pKa value, for example this one, higher the pKa value, they are less stable, which means my OH minus is less stable. Lower the pKa value, they are more stable. This particularly in case of this anion or conjugate base. When the conjugate base is stable, the pK is low. When the conjugate base is unstable, the pK is more. Okay, so this is another example I have given you. Just consider the pK value of butane. Okay, if you take the butane, N-butyl lithium, you probably heard somewhere that one of the terminal CH bond is replaced with the lithium. Okay, so you have CH3, CH2, CH2, CH2 minus and lithium plus. The pK of this is 48. That means that my CH2 minus is highly unstable. So if it is unstable, the pKa value is very high. If it is very stable, the minus conjugate base, if it is very stable, the pKa value will be less. Okay, so what does it mean here? The less value means they are very stable. This particular conjugate base is very stable, or anion is very stable, which means this minus charge is distributed. Somehow it is stabilized by resonance with, because the sulfur is connected to the two oxygen with the double bonds. So this O minus will having resonance stabilization with that two of the SO double bonds. Okay, so this is, which means that the negative charge is not available to donate to the carbon center. In the other case, when you have hydroxyl anion, this is actually highly unstable. The electron density is there on the oxygen and it can easily donate to the carbon center, and that's why when you use that nucleophile like OH minus, the reaction is very fast. When you use carboxylate, you can see the pKa drops down to 4.7. It is moderate. Now when you go to the water or like sulfonate, the reaction is very slow. Okay, so here when you compare with the oxoanions, I should say oxoanions, or yeah, oxoanions, then you should see their acidity. Okay, always remember the acidity. More acidic means pK value is less, they are less reactive, or less acidic or more basic. More basic means pK value is very high, their reactivity is very high. So you remember that. Second category, we are going to talk about this halides. Okay, so we have seen earlier, I mentioned that halides can be living group as well as nucleophile. Okay, now how this is taking place. Now if you see here, the fluoride, the pK value is high. Okay, 3, -7, -9, -10, which means the acidity increase when you go down. Now what we have seen here, when the acidity increase, okay, the reactivity slows down. But here, when the acidity increase, the reactivity increase. So the reason is completely different. The explanation is completely different. So here the acidity actually we consider the stability of the anion, yeah, carboxylate or that oxoanion. Here the acidity depends on the hydrogen and halogen bond, HX bond. Okay, particularly the HX bond. So here the HX bond is very weak, so that's why the acidity is very high. So it is not actually the stability of the anion. Now even though we say that the halide, the iodide is very large molecule, a large atom, yeah, or anion I can say, but the reactivity is very high. Why it is so? First, think about the electronegativity. Okay, so in case of fluorine, fluorine is the most electronegative element. Okay, so therefore it will hold its electron tightly closer to the nucleus. Okay, so it will not give or wish to give away its electrons. Okay, so if for example you're holding something very tightly, yeah, so if somebody used to take it, he has to work a lot to take it away from you. Yeah, so the same thing, the fluorine is the most electronegative element. It's holding its electrons very tightly closer to the nucleus, so it will not wish to donate the electron. Okay, so that's why, that is the this very simplest reason to understand that why fluorine is the bad nucleophile. So you will hardly see that fluorine is a nucleophile. Okay, okay, then chlorine, so you increase the you decrease the electronegativity, you increase the nucleophilicity. For the bromine, you again decrease the electronegativity, you increase the nucleophilicity, and that goes on until the iodide. This is another reason. So which actually you might not see often in different books, but actually it says that what I said earlier, that in case of SN2 reaction, the nucleophile attack the carbon center in the anti-bonding. Okay, the anti-bonding. Now when you have an anti-bonding, the energy is very high. Yeah, this energy of the anti-bonding is falls very closer to the 5p orbital of the iodide. Okay, so the anti-bonding energy and the 5p orbital very close, and then their overlap is very nice. Okay, so always remember, when you draw the molecular orbital of a molecule, okay, so if the energy of the orbitals are very close, then the overlap is very good, the bond would be very strong. The same thing here, that why the hydrogen and iodine bond is very weak, because hydrogen is 1s, iodine is 5p, so therefore the overlap is very bad overlap, and that's why they can easily ionize. Okay, that's why the acidity is very high. And the same thing here, because it is very high in energy, 5p orbital, and the anti-bonding is very closer to that, and therefore the overlap is very good. Okay, the anti-bonding of the carbon and leaving group and the 5p orbital of the iodide, they will overlap very efficiently, and therefore reaction is very fast. Okay, so you should not confuse with these two explanations. Here we discuss about the stability of the anionic species, that actually means that electrons are not available for nucleophilic attack. In this case, it is actually the electronegativity. In first case, second is the orbital overlap, that's coming later, but the electronegativity of the halides, the electronegativity of the fluoride is very high, or it is the most negative element, and it will not wish to donate the electron. So therefore the nucleophilicity is very poor. And in case of iodide, it is the least electronegative halide, so therefore it can easily donate its electron. Okay, I hope you understood that part. Let's move to the other nucleophilicity of another anion. So for example, selenium, sulfur and oxygen. So if you look at that, whatever I have discussed in the previous slide, that the oxygen, sulfur, selenium, so you go down and down on the periodic table, particular group. Okay, then what you will find is that when you go down, that nucleophilicity increased. Okay, and that is because it is getting closer to the antibonding. Okay, the same thing nitrogen and phosphorus as well. So phosphorus substrates are more more or better nucleophile compared to the nitrogen, and so that is the homo-LUMO interaction. Okay, so this nucleophile orbitals should be very closer to the LUMO of the carbon and leaving group bond, and there the orbital overlap will be better. Okay, so that so far we have discussed. This is a pictorial diagram, that this is the sigma bonding and this is the sigma anti-bonding. This is very high in energy, and when you go from going from oxygen, sulfur, selenium or fluoride chloride, bromide, iodide, you are getting closer to the anti-bonding, and therefore the overlap will be better and the reactions will be more facile, or it will be much faster. Okay, so that another thing that we will be discussing here is that amphiphilic nucleophile, or ambident nucleophile. So ambident nucleophile, it's also follows SN2 mechanism. Okay, so ambident nucleophile are those which are two or more atoms bear an unshared pair of electron. Now, what does it mean is that you have a nucleophile. Okay, you may have two different centers where you will find there are electrons. So this can act as a nucleophile, or the other one can act as a nucleophile. So how you can balance this? Okay, so let's give an example here. So if you have this particular compound, so this is methyl acetoacetate. Okay, this is called methyl acetoacetate. If you treat with the base, you can produce a anion over here. Now if you react with the alkyl halide, so this is a nucleophile, it will replace the halide, you can get the particular compound. Okay, but this anion, this can be like tautomerized to oxygen. Okay, this can go over there as well. So either it can go this side oxygen, it can go that side oxygen. So your oxygen can be nucleophile here, O minus, or this O minus can be nucleophile as well. Okay, so I can also show you that this proton, okay, this can be you can also produce a negative charge over here. Okay, so you can also have a reaction over there. Okay, but if you choose the the nucleophile as a base properly, so because the acidity of this proton around 17, whereas this one is around 30, so if you use a base which is which having the pKa value about like 20 or less than 20, you only deprotonate this one but not this one. So there is a different issues. So but in principle you can also produce anion over there. So basically you have one anion over here, one over here, one over here, one over here. So you can see for this particular compound you can have 4 different anions, but which one will be reacting? That is very important point. Yeah, so let's take an example of aromatic reactions. Okay, and that is actually, so what I just forgot to mention, the reduced selectivity can be tuned using different solvents. Okay, so solvent will play a very vital role in deciding to decide which center will be the nucleophile, which will be not. Okay, so this is the example that is actually experimentally known or proved that if you use this particular, what is that, beta naphthol, yeah, beta naphthol with the we can say that is the phenolate, not phenolate, which is deprotonated. Okay, so when you react this particular compound with the benzyl bromide, you can get two products. One, the reaction occurs on the oxygen atom or via the oxygen atom. Another one occurs through the carbon center. Okay, so here it is called O-alkylation. So this product is a O-alkylation. You alkylate at the oxygen position, and this is called C-alkylation. The reaction occurs at the carbon center. Now you see, when you use DMSO, okay, you get mostly the O-alkylated product where the reaction occurs through the oxygen. However, if you use that ethanol, 2,2,2-trifluoroethanol, okay, you get 85% at the carbon center or the C-alkylation and only 15% at the oxygen center or O-alkylation. So you see that by changing, so this is your polar but aprotic solvent, this is polar protic solvent. Okay, so if you change this, you can actually change the product ratio. Now why this is happening, let's try to understand that. Okay, so for example, let's take an example that you are going to a concert. Okay, you are in a concert, you are just about to enter the field, you are just at the beginning of the field, and your stage where the star is having singing or performing, whatever it is at the other end of the field. If nobody is there, you can easily walk through the field and you can reach the stage or dais. If the field is completely crowded, if you want to reach that dais, you have to take another way. Yeah, this is very simple to understand. Now come back to this example. In a polar aprotic solvent, first take the polar protic solvent. Polar protic solvent is actually we having a OH, yeah, that is a protic. So which means that OH can be easily ionized and you can have like a O minus and H plus. Okay. In case of polar protic solvent, the polar protic solvent forms very strong hydrogen bonds with this oxygen. Okay, so what you can see is that if I try to uh, draw like this, I don't know how can I draw it better now. So if you have all these R, okay, so this kind of molecule will be surrounding the O minus in polar protic solvent. Okay, so when this is so many of your solvent is surround that O minus, okay, it's similar to that you are standing one end of the field and the field is completely crowded. Okay, so this crowd is actually the solvent molecules for this oxygen, but it wants to reach the reacting center, yeah, the carbon center for reaction. So it is not able to go through the field, but rather it go via the carbon, yeah. So it takes another way to reach the the benzyl bromide. You got it? So that solvent molecule is actually crowd for you to reach the dias. Okay, so in polar protic solvent, you have huge number of solvent molecule that surrounds the O minus. So it will having a difficulty to reach the benzyl bromide to react. Therefore, it takes a different path and reach the benzyl bromide, and that path is the carbon. So you do the C alkylation, not carbon alkylation. In DMSO, you do not form this kind of hydrogen bonds because there is no polar. I say this is polar but aprotic solvent, so there is no protons, so you do not form the hydrogen bonds. If there is nothing around it, like the empty field, it directly attack there. Okay, so that is, I think that is a very nice analogy to understand it. Yeah, I hope you understand that one. So that is the end of the SN2 reaction. Okay, so after that we will be discussing SN1 reaction. Okay, okay, so let's start.